Hamiltonian formalism. Okay. So, we need some more energy for this one. So, the way we write Hamiltonian for particles, we can write Hamiltonian for fields. Okay. So, momentum density, right, we have momentum no for particles. So, what is this dl by dx dot, partial L partial x dot. So, instead of that we have partial L, not partial, okay, it is a functional derivative. Now, L is a function, so we get partial L partial delta L delta phi dot. Now, I is a component, it could be x component, y component, g component, I get partial L partial phi dot. Okay. Now, this is now L is integral L d4x. So, when I go inside, then it is going to be partial. When I am, so this is total L d cube, not d, sorry, d cube. So, total L I have to do the functional derivative because it is function of any phi, but when I go inside, this Lagrangian density is function of phi, then I do partial derivative. Okay. Now, that is momentum. I defined, this is the definition, Hamiltonian density is pi I, this is pi I dot minus L, is very similar to what we do for particles, pi xi dot minus L. Okay. And we define total Hamiltonian is integral over space. Okay. So, now equation of motion. So, like we have x dot is derivative of h with pi dot. So, we have phi I dot equal to partial h, no, there is no derivative, this is old slide actually, delta h delta pi I, and we have pi I dot is delta h delta phi I. Okay. So, I think I have an example. So, we have this example. For this I am going to write down the Hamiltonian. Now, this is Lagrangian, Lagrangian is function of phi dot, but Hamiltonian is function of phi and pi. Okay. So, this dot is not there. So, delta L delta phi, no, so this dot is there, this dot is there, sorry, this dot is there, delta L phi I dot, like delta L delta xi dot is there, no, for and that is you will act on derivative, which is phi I dot, this one squared. So, you take the derivative, I will get phi dot. Okay. So, pi is nothing but phi dot, which is like momentum is x dot, very similar, the formalism is in fact motivated from particles. So, Hamiltonian will be pi phi I dot minus L. Now, pi is nothing but phi dot. So, this guy will give us okay. So, what will I get, phi dot into phi dot, which is phi dot square, minus this one, minus half phi dot square, that is this one. Okay. Then this minus minus becomes plus, so plus grad phi square plus v phi. Okay. Now, phi dot is nothing but pi. So, this is my Hamiltonian density. It should be function of pi and phi and grad phi's, but not phi dot. Okay. Do not write phi dot for Hamiltonian. The way for particles we do not write x dot when Hamiltonian, we write only momentum. Okay. So, equation of motion. So, phi dot is delta, this is not there, delta h delta pi I, and I equal to 1 for this is 1d. So, this is going to give us phi dot equal to delta h by delta pi will be pi. Okay. Now, this is not dot here. So, pi dot is delta h by delta phi with a minus sign, there is a minus sign here. Okay. Now, so we get delta h by delta phi. So, this is the functional derivative. Okay. So, functional derivative, I again apply the logic of functional derivative, is function of the derivative phi as well as grad phi will come. Okay. Both the terms will come. So, I get partial h partial phi minus this divergence of partial h partial grad phi. Okay. This will come, and this one is this Hamiltonian. So, function of a derivative with phi will give us, will come from here V phi. So, that is V phi, and partial H partial grad phi will give us grad phi here, and divergence. So, divergence of a grad is Laplacian. Okay, that. So, this is pi dot, okay, pi dot, and pi dot is, well, pi is phi dot. So, this is nothing but pi double dot, or this it is square, okay, right. So, that I am just using this relation. So, this equation, okay. So, field with a potential, the equation Euler Lagrange equation is this, okay, and there are potential, there are, in fact we will encounter fields with potential, okay. You might have seen the free energy, for phase transition is phi squared minus phi 4. So, these are the potential, okay, and so this is the example. I think I will do the other example later, because I think it is already close to saturation. So, this one is a quite important one. So, you can write down Lagrangian for a Schrodinger equation, non-linear Schrodinger, non-relativistic Schrodinger equation, and I will do it in the next class. In fact, I think we need to spend some time on it. So, we will do it in the next class.